Okay, so we're continuing with the first few lectures, which are introducing graph theory. And so for the first part, and actually most of today's lecture, we're going to talk about a particular type of graph called a bipartite graph. Right. And so what are bipartite graphs? They're loosely speaking, they're graphs where you can separate the set of vertices into two disjoint parts, such that within each part there's no interaction. And by interaction, I just mean incidences or connections via edges. And so a simple example of this type of graph, before I write down the more formal definition, right? So maybe over here I have some collection, right? So I'll have some graph G with some collection of vertices and some collection of edges, and we'll assume it's simple, meaning there's no loops. And so maybe I'll have some collection of 3 vertices, which I'll call A, B, and C. That's V1. And then maybe I also have some other subset of V, which I'll call V2, of say D, E, and F. And so a graph is bipartite if, well, there can be edges connecting vertices from V1 to V2, right? So maybe A is connected to D and E, B is connected to E, C is connected to D and F. But notice there's no interaction or connections between A and B, or B and C, or C and A. And similarly, there's no interaction between D and D, or D and F, or E and F, right? And so there's no incidences, meaning edges that connect vertices among V1 or among V2, right? And so this is an example of something called a bipartite graph, where again, you can split the set of vertices into 2 parts, and in each of those parts, there's no interaction, meaning no connection by edge. Right, so let's write down the formal definition then. Right, so a simple graph G, right, with some set of vertices and some set of edges that connect the vertices, is bipartite if the set of V can be split or partitioned as a disjoint union of 2 sets V1 and V2 in the sense above, with the conditions that we saw in the previous example. So partitioned into, into disjoint sets V1 and V2, such that every edge connects a vertex from V1 to a vertex in V2. Right. Right, so each edge E in the collection of edges connects some vertex in V1 to some vertex in V2. And moreover, there's no edge that will connect 2 vertices in V1 to themselves, or connect a vertex in V1 to another vertex in V1. And there's no edge that will connect a vertex in V2 to another vertex in V2, right? So let me just put that in the parenthetical just to clarify. So no edge connects 2 vertices in V1 or 2 vertices in V2. Right, and so with this definition in mind, the example on the top of the page is an example of a bipartite graph. And again, notice that all the edges are connecting something from V1 to something in V2, and there's no edges that connect the vertices in V1 to themselves, or there's no edge that connects some vertex in V2 to another vertex or vertex in V2. Right. So this is the basic definition of what a bipartite graph is. And so these types of graphs typically show up in models when you're looking at, for example, maybe V1 is a collection of people who are applying for a particular job, and V2 is a or applying for multiple jobs, and V2 is a collection of possible jobs for which these people can be hired. And these graphs represent maybe each edge is like a preference from the person in V1 to the job in V2, and the graph models like what people prefer and gives like a good representation of the different jobs that different people prefer. And so, of course, a person is not applying to another person, right? Another person is not a job, so there's not going to be any connection between person A and person B, for example. And likewise, it doesn't make sense for there to be connection between between different jobs in this model. And so this is one situation where these would arise when you're modeling sort of this type of job matching problem, which we'll talk about a little bit more later on. But first, I want to just a little bit more abstractly just look at some examples of things that are bipartite and are not, and talk about how do you actually check if a graph is bipartite, right? Because in the example I drew up here, it's pretty easy to see, but it doesn't have to be laid out in such a nice way, right? So you could just be given an arbitrary simple graph. And so how do you check that it's bipartite, meaning how can you check if there can actually be a partition of the set of vertices into V1 and V2, right? So that's what we'll be looking at. So let's first look at an example of something that's not bipartite. So remember, let me look at the complete graph K4 on 4 elements. And so this looks something like this. Right, and so let me label these vertices as A, B, C, and D. And so this is not bipartite. Right. And what's one way to see this? Well, let's just look at the vertex A, right? So note that A is connected to all of the other vertices, right? So it's connected to B, C, and D. So if I try to make a chart, right? So my vertex set is the set A, B, C, and D. If it were bipartite, I should be able to break up V as V1 union V2, where these are disjoint, right? Well, what is my candidate for V1? Well, let's say A is in V1. Well, notice that since A is connected to B, C, and D, I can't put B, C, or D into V1, because then I would have an edge connecting elements of V1, which I'm not allowed if I want to be bipartite. And so therefore, if there was such a decomposition, I would have to put B, C, and D all in V2. But the problem is that well, these are connected to each other, right? Right, and so therefore, this, if I go back to the previous definition, well, remember, we're not allowed, if it were to be bipartite, we're not allowed to have edges connecting things in V2. But we just showed that the only way to make this work is if we broke up the vertices in the way I have here, and therefore, well, it can't be done, right? Because in the set V2, there necessarily have to be edges connecting these elements just based on the picture, right? So this is not bipartite. Right, and so the general problem that I want to address first is, right, let's say you're given a graph G that's simple. And so the question is, well, how do you determine, how can you check if it's bipartite or not? Right, so how to check. Right, and so I don't know if there's any sort of like rigorous algorithm to do this, but what you can do, as long as the vertices have, as long as you're given a graph with a relatively small number of vertices, like less than 100 or something like that, what you can do is just sort of approach it in the same way I approached the last example, right? So just pick, right? So what you want to do is sort of maintain a list for a possible choice of V1. Right, and so just begin with one vertex, right? In the last example, we fixed A and put that vertex in V1. and then everything that A is connected to has to belong to V2, right? So I can do this process where I put one vertex in V1, and then everything it's connected to, if it were bipartite, I would have to put those in V2. And then once I do that, I move on to the next element that hasn't been covered, and you keep doing this until you hit everything. And then you can check if the thing that you result with does actually meet the conditions that are required. And if it doesn't, then the graph can't be bipartite, right? So, right. So let's actually demonstrate this with an example. I think instead of writing it out more abstractly, it's easier to just see. Right. So let's suppose the graph we're given is the following. So just give me a second to write this out. Right, so this graph is going to have 6 vertices, E and F. Right, so this is my G. And so in this case, my vertex set is A, B, C, D, E, and F. And so the question, well, is this bipartite? Right, and so again, how are we going to check? Well, let's begin by trying to list some candidates for V1 and see what that forces us to put in V2. So let's just begin with A. So let's say we put A in V1. Well, then everything that A is connected to has to be put in V2, right? Because I'm not allowed to have anything else in V1, any other vertices in V1 that A is connected to. So necessarily, if it were bipartite, I would have to put E, D, and C into V2, right? Right. And so, well, notice that there's no connection between E and D. There's no edge connecting E and D. There's no edge connecting D and C. And there's no edge connecting E and C. And so there's currently no contradiction. So we're on the way to guessing that maybe this is bipartite. And so one thing that's actually helpful is maybe I can color the vertices according to which collection they're in. So let me color them, let's say red if they're in V1 and blue if they're in V2. Right, so we're putting A in V1 and E, D, and C are in V2, right? And you can, I mean, if you use this coloring, you can see that it helps sort of understand what the partition should be, right? So what's left uncolored? Well, I have B. Notice that B is not connected to A, so I can put B into V1 without losing the assumption that this is while maintaining the property I want for it to be bipartite. And similarly, F is not, you can see that the F is not connected to any of the other red vertices, right? F is not connected to A and F is not connected to B. And so then we see that, okay, I can put B and F into V1, right? Well, this is a partition, right? I've covered everything, right? And these are disjoint, right? And so this graph is bipartite, right? So G is bipartite, right? But notice that this was not like a trivial thing to check. We had to actually go through all the vertices and double check everything. So some of the examples you're gonna have to, again, you're gonna have to do this process, right? It may not be obvious that it's bipartite. And so notice that if you do this coloring approach, right, where I'm coloring the vertices, notice that, like, for example, look at A, where I have a red dot. Well, notice that every vertex that's a neighbor of A has a blue dot, right? So there's no neighbor of A that has a red dot. And then, well, look at a blue dot. For example, look at D. Well, every neighbor of D has a red dot, not a blue dot, right? And so it turns out that this way of coloring the vertices actually characterizes when a graph can be bipartite. So this is an example of what's called like a coloring theorem. And the theorem is the following. So a simple graph G, say with vertex set V and edge set E, is bipartite, if and only if, meaning it's equivalent to, so if and only if you can, there's a, sorry, you can color the vertices, say red and blue, such that no red vertex is a neighbor of another red vertex, and no blue vertex is a neighbor of another blue vertex, right? So, such that no vertices of the same color are adjacent. Right, and so, right, so what's we saw sort of why this was the case in the last example. What's the idea of the proof, which is basically the full proof, right? So if I had, right, let's say we first know that the graph is bipartite, right? So if I have a partition V1 and V2, right, you can just label, let's label all of these red and label all of these blue, right? And so if it's bipartite, well, nothing in V1 can be connected to anything else in V1. So none of the red vertices can be connected to another red vertex, right? And so therefore, you can color it this way, and there no vertices of the same color will be connected to one another, right? And so this is the main idea of the proof, right? And on the other hand, if you were just given a graph that already had this coloring, well, it tells you how to find V1 and V2, because you would just let V1 be the red dots and V2 be the blue dots, right? So that's basically the proof. And so remember, I actually don't know if we've gone through this, but remember when you see if and only if in a statement, this is a statement of like logical equivalence. And so when you have to prove an if and only if statement, you actually have to prove two things, which is basically what I just outlined verbally, but maybe when we come to proofs that I'm going to go through in more detail, I'll come back to this point. Right. Okay, and so let's look at another example. Sorry. Right, and so once again, we'll look at an example of a graph and try to see if it's bipartite or not. So in this case, right, just give me a second to write it out. So say this is vertex E, or sorry, A. This is vertex E. I have G over here. B, and B is connected to F, and say G is also connected to F. I also want B connected to E. And then finally, there's a point D out here, which is connected to E. Right, so this is my graph G. And so the question is, well, is G bipartite? Right, and so once again, what we want to do is just start with a list of candidates for V1. So let's begin by putting A into V1. Right, well, if I put A into V1, then I have to put everything that A is connected to into V2, right? So I have to put E into V2. And so you keeping this coloring idea in mind from before, let me color everything in V1 with the red. So right, let me color A with red, and let me color everything in V2 with blue. Right, so I'm coloring E with blue. Right. Well, notice that if this were bipartite, I'm not allowed to have E connected to any other blue vertices. So therefore, well, what is E connected to? E is connected to G, and E is connected to B, right? So I would need to put G and B both inside V1, right? Right, and this is again because E is connected to both G and B. But now we have a problem, right? Because if I look over here, well, we have two reds connected, right? So G and B are connected to each other, but I'm forced to put G and B both into the red collection or into V1, and so therefore it can't be bipartite. right? Because I just did the only thing I really could do, and we came to a scenario where we were forced to put both G and B into V1, even though they're connected, or even though they're both colored red. And so therefore, this example is not bipartite, right? And so in general, this is how you should, if you're given a graph and you need to check if it's bipartite, this is how you should do it. If it helps to use colors, you should like use different colored pens or something like that to keep track of everything. Right, and so briefly, as I mentioned before, where does this often show up in practice? So bipartite graphs usually show up as examples of matchings, for example, job matchings. And so what is the more rigorous definition of a matching? Right? So let's say we have a simple graph G, which I'll call, again, label with V and E. And so a matching is a subset of the collection of edges, right? So a subset of V such that no two edges are incident with the same vertex. Right, so maybe I have some vertices over here, say A, B, and C, and say D and D over here. And so if this is a matching, well, maybe A is connected to E. Right, and so then if I have an edge leaving B, I'm not allowed to have B connected to E, because then I would have two edges that are incident with E, right? So maybe B is connected with D, and then I'm not, if this is a matching, I'm not allowed to have C connected to anything. Right? Right. And so one place where this shows up is, for example, let's look at the preferred job problem. Right, and so suppose we have a list of job candidates, and suppose we have a list of the preferred jobs that they want, right? So say we have candidate A, B, C, and D. And then we have jobs, say 1, 2, not being very creative, just labeling them with numbers, 1, 2, 3, and 4. And say, right, so let me use blue edges to represent jobs that they want. Right, so let's suppose person A likes job 1 and also likes job 3, and maybe person B likes job 3 and job 4, or yeah, job 4, and say person C likes 1, 3, and 4. Okay. And then finally, let's say person D likes 2 and 1. Right. And so we get this complicated looking graph, which is bipartite, right? Because I'm not connecting any of the job candidates to other job candidates, and I'm not connecting any jobs to other jobs. Right. And so this is not a matching as it's written, right? Right, because I have lots of different edges that are, like I have an edge from A that goes to 1, and I also have an edge from C that goes to 1, and an edge from D that goes to 1. So if it's a matching, then I need only for each job, there should only be one person matched to that job. Right. And so, well, let me make this a matching by assigning a job to each person so that no person is assigned to or no job has more than one person assigned to it. Right, and so we'll notice there's only one person who wants job 2, and that's person D. So let me assign D to person 2. right? So I'll use red to denote the matched job. Right, let me say, let's assign person C to job 4, right? Let's assign person A to job 1, right? And then let's assign person B to job 3, right? And so if we look at this picture where we have A, B, C, and D, and then 1, 2, 3, and 4, right, so we had A connected to 1, we had D connected to 2, B3, and C4. So this is a matching, right? Right. And so this is an example of something called a subgraph of the original graph, which we'll talk about more later on today. Right, and so this subgraph in red, which is like a graph that's contained in the larger graph, is an example of a matching. Right? And in fact, this is something that's called a complete matching, meaning that every vertex is, every person has been assigned or matched to a job. Right, so let me just write out that bit of terminology. So a complete matching is a matching where every vertex in V1 is matched. Right, and by V1 I mean all the vertices that are on the left part. Right, and so a general problem in applications is, well, I mean, this problem of matching people to particular jobs is something that has to be dealt with in the real world. For example, in the university setting, you have a group of faculty, and you need to be able to match each faculty to a particular course that they're going to teach. Without, you can't have two people teaching the same class, right? And so the problem is, well, how do you know? Let's suppose that you have a graph G, which is simple and bipartite. Right, and so the problem is, when does there exist a complete matching, which is sort of like a satisfactory matching on the graph? Right. And so this problem was mathematically resolved in the 1950s by Hall, and so this has this is a theorem that characterizes the solution to the problem, which goes by the name of Hall's marriage theorem. Again, just to connect to the matching problem, right? Right, and so the theorem is that suppose you have a bipartite graph, which is simple. I guess it's built into the definition of bipartite that it's simple, so I don't have to keep repeating that. Well, this graph has a complete matching if and only if the following quantitative property holds. So if and only if I look at any subset A of the first vertex set V1, right? So for all subsets A of V1, if I look at the cardinality of the neighbors of A, then there are at least as many neighbors associated to that set as the cardinality of the set. Okay. And so again, what does this mean? Here we're seeing this phrase if and only if show up. So this has two logical statements in it. So the first is, if your graph has a complete matching, then necessarily this property about the set A must hold, right? So if you have a complete matching, then for any subset of the set V1, the cardinality of the neighbors of A has to be at least as large as the cardinality of A. On the other hand, it also says that if this quantitative property holds, so if you know that for any subset of V1, the cardinality of the neighbor set is at least the cardinality of A, then you can construct, or you can always find a complete matching, right? right? So if and only if means that the first statement is logically equivalent to the second. So that means that the first statement should imply the second, and then the second should imply the first, right? So in order to prove this, you have to prove two things. You have to prove that if you have a complete matching, then this inequality holds. And then on the other hand, you have to prove that if this inequality holds, then you can always find a complete matching. Right. And so the proof, which I'm going to omit from the lecture because it would take a lot of time, and I think it's a little bit difficult for the second lecture in graph theory, although it's not out of reach. So it proceeds by induction on the size of V1, strong induction. And so this is one of those induction proofs where it's not a straightforward argument. Like you need to be a little bit creative, and it requires some ideas. I mean, this is mathematically this is a relatively new result because it's only about 70 years old or something like that, right? And so I would recommend it if you're interested, try to read the proof in the book. It's written out, but otherwise I'm omitting it from the lecture today, just because we want to keep introducing some more basic graph theory terminology, things like that. All right, so if we go back a few pages, so notice that we had this list of job candidates and preferred jobs, and then all these blue edges, and then I selected a certain subcollection of red edges, which gave me a complete matching. And so we remember we produced a new graph, which is called a subgraph, right? And so what we're going to do now is actually define more formally what is a subgraph of an arbitrary graph, and go through all of that. Right. So we just saw one example of that. Right. And so this is the final part of section 10.2, which is basically the broad introduction to graph theory, right? And so we're going to talk about how to construct new graphs from given graphs, or new graphs from old graphs. Right. And so well, we already saw one example with this job graph, and then we had a smaller graph obtained from it, which was the complete matching. You can look at simpler examples, right? So for example, let's say I have the complete graph on 4 vertices, which is K4, right? So it looks like this. Well, if I just look at the graph where I just draw the square, right? There's some sense in which this is contained in the first. Right, so this is K4. So this is somehow contained in K4, because if I just delete the X in the middle, I get this graph. And similarly, well, if I delete the edges that make up this square and leave in everything else, right? So I would get this graph that looks like an X, right? And so both of these things look like they're contained in K4. So they're somehow like smaller graphs that are embedded inside of K4. And so both of these are also examples of subgraphs. Right? So instead of subset, they're subgraphs, right? But otherwise, it's the same idea. Right. And so what's the definition? Right. We don't want to just keep using intuitive notions, right? You want everything to be defined very, very precisely. So let's suppose I have a graph G. So another graph, say H. Right, so let's say H has vertex set W and edge set F, right? So the vertices are W and edges of H are in F. So such a graph H is a subgraph if, well, what's the natural way to do this? Well, I notice in the picture above, the collection of vertices in the two graphs on the right is a subset of the collection of vertices of K4. And also the collection of edges is a subset of the collection of edges, right? I'm not adding any new edges that were not in K4 in that example. And so these are the two conditions we'll require. So it's a subgraph if the vertex set W is a subset of V, where V is the vertices from the original graph G, and also this collection of edges is a subset of the edges of G, right? So it's a subgraph if the vertices of H are a subset of the vertices of G, and if the edges of H are a subset of the edges of G, right? And you can check just looking at the example above that both of these conditions are met. So these are both subgraphs of K4. Right. And so another example, well, let's suppose finding a subgraph. Let's suppose G is just any graph. Right. And so if I just delete some edges, right? So let's say E, let's call E with a tilde some subset of E. And suppose I let F equal E minus E tilde, meaning I take the complement in E. And then let's define H to be V comma F. Which is the same, where I'm not changing the vertices and I'm just modifying, deleting some edges, right? So this is always a subgraph, right? And it just follows right from the definition because F is clearly a subset of E because I'm just removing some things from E, so it's some subset, right? And so, for example, right, let's say this is G. And let's say I remove the edge connecting D and D, and I get a new graph H. Right, and then so let's say I remove this edge, so now D is an isolated vertex. Right, so this is a subgraph. Right. You may also think, okay, well, I should be able to also remove D. And in this case, if I also remove the vertex D and I just left myself with this triangle connecting A, B, and C, that would also be a subgraph. But if you just try to construct a subgraph from a given graph by just removing a bunch of vertices, if you have a more complicated graph, you're going to run into some problems because you also have to make sure you get rid of all the edges that are incident with the vertex that you remove, right? Otherwise, you'll have an edge that's not connected to anything, and so therefore it's not really a graph, right? So for removing vertices, you can construct subgraphs by removing vertices, but you have to be a little bit careful. Right, so let me just write out what has to be done. Right, so suppose V is a vertex in the graph G, right? So G minus the vertex graph V is defined to be the graph obtained by removing V, whatever the vertex V was, from G, and also removing all edges that are incident with V. Right, you can't just remove the vertex if you want to make a subgraph. You have to also remove all the edges that connected it. Right, so for example, let's suppose we do in the picture above, let's look at G minus B. Right, so what is G minus B? Well, I want to remove B, so I'm only going to have A and D and C. Right, I've removed B, but I also have to remove all the edges that are connected to B, right? So there are two edges that are connected to B, which I have to delete. And so I'm just left with this, right? So I just have the edge connecting A and C, and then D is just left as an isolated point. Right? Okay. So you can still construct, the first example shows you can construct subgraphs just by removing whatever edges you want, and that's always okay. The second point is that, well, you can construct a subgraph by removing vertices, but whenever you remove a vertex, you also have to remove all the edges that are connected to it, or else you don't end up with a graph, right? And so that doesn't work. Okay, and the final thing I want to talk about. So this is a introduction to subgraphs, and now I just want to talk about one operation you can do with graphs, which is taking their union, and then we'll be done for the day. Right. So what is the union of two graphs? So let's say I have one graph G1, which is V1 E1. Right. So the vertex set for G1 is V1, and the edge set is E1. And then I have another graph G2, which has vertices V2 and edges E2. So how do you define the union of the two graphs? Well, there's really only one way to do it, right? You combine the vertices, take the union of the vertices, and you also take the union of the edges, right? And so this is what the definition of the union of two graphs are. And so it'll help to just look at one picture to see what this looks like. So let me have my graph G1 be the graph where the vertices are U, V, and W. And let's say G2 is the graph with vertices, right? So it's possible that G1 and G2 can have some of the same vertices. So maybe V is also a vertex from G for G2. And the other vertices are A, B, and C, and they're connected in this way. Right. And so what does the union look like? Right. Well, I have to combine, I'm taking the union of the vertex sets. So in this case, V1 union V2. Well, I'm going to have A, B, C, V, U, and W. Right. So those are my vertices. Right. So let's write those out. So maybe U, V, W, A, B, and maybe C is over here. And then I also want to include all the edges, right? So I have an edge from U to V, edge from U to W, and edge from V to W. But I also, if I now look at G2, notice I have an edge from A to V, so I have to include that. And then, right, let me add in the others, right? So this is the union of the graphs, right? So we join them together and to make one larger graph. Right? And so one thing that's worth pointing out is that each of these graphs is a subgraph of the union. Right, where I is equal to one or two, right? And so that just easily follows from the definition because, well, what are the vertices of G1? That's V1, and the V1 is clearly a subset of V1 union V2, and E1 is clearly a subset of E1 union E2, and so G1 is a subgraph, and similarly G2 is a subgraph. Okay, and so that finishes up the main stuff we want to talk about from section 10.2. And so in the next lecture, we'll move on to talk about graph isomorphisms, which are a way of demonstrating or checking if two graphs are basically containing the same information. And so this is actually a very complicated problem. So we'll spend some time talking about that. I do want to point out also that I've chosen to mainly focus on mathematical content and not talk too much about applications of graphs beyond some of the simple applications we talked about today, at least for the first several lectures, just so that we can get through the most important points of the mathematical content of graph theory, because we only have a finite amount of time, and if I spent more time talking about all the applications, we wouldn't be able to get to some topics that we should get to. So if you're interested in how this stuff is applied, as we're learning this stuff, there's lots of examples in the book where the book will pause developing the math and go through lots of interesting ways in which graph theory is used in outside of math. And so I would recommend reading those along as you're watching these lectures if you're interested in applications. It would be nice to include this stuff more in the lectures, but again, then I wouldn't be able to cover everything we're supposed to. So, right.